All right, so now you believe me. Okay, here we go. So now, this is all interesting. How can we possibly do homework on this? So now we'll do a homework problem on this. Here we go. I want to show you how to use this thing mathematically here. Let's see. What does mass density mean? Mass density is the mass per unit length of the string. So that's why it's in kilograms per meter. So I took that string, and I cut a meter, and I took it to my lab, and I put it on the scale, and I got the wrong number because it wasn't stretched yet. So I took the string and stretched it and said this much is a meter when it's stretched, and I took it and it unstretched, and I weighed it in my lab, and that's really a meter once it's stretched, and I took that mass over a meter, and that's what that is. So it's literally just a measured mass per unit length, but it changes when you stretch it, so it depends on the tension. So, okay, so let's do a wave example. Right, so in this example, you're just going to they're going to draw you a wave. Here's a wave where you're given the graph. It's a function of position. This we're just going to call y. We're not even saying it's a string. It's just something happens in the y. Maybe it's position, maybe it isn't. And we're going to draw it as a sine. Looks like a sine wave. And it's going to go up to 2. And let's go down to -2 and whatever x is, who knows. And this first thing is going to happen at 1.5 meters. And then this second thing crossing here is at 3 meters at this instant in time. Right? Since there's a wave equation, this thing's actually flying to the right. So I think we're going to say, well, this is, say, t equals 0. Okay? So that's not quite everything you need to know about the wave. You need to know something about time. Right? You know nothing about time here. All you know is the shape at some time. So you know how fast it's going. We're also going to tell you that the whole thing is moving at 6 meters per second. So this is a test of do you understand how to use the equation and the real relationships. So over here, while you're thinking about that, somebody asking, why did you divide by 50? Because the video was slowed down by 50. So it was literally 3.33 seconds in a video that was slowed down by a factor of 50. So it was actually a lot shorter than 3.33 seconds. Yeah, it was for fun, really. Okay, so we want to write the equation. So here, A. Right? The wave, it's really not the wave equation, it's the wave solution. The wave equation is that differential equation we wrote down last time. We want the solution, A sine kx minus omega t. Okay, so I would say, well, I would call it this. A is what? That's the first one you got to know is what is A? 2. Amplitude is 2. Okay, so we say, okay, y for all position and time, 2 is the amplitude. And then, do you want to use a sine or a cosine? Okay, everybody gets to vote. 1, 2, 3, sine. Let's use a sine because at time equals 0, it looks like a sine. And then we won't need a phase. If we describe this with a cosine, it's actually a cosine shifted. We don't want to deal with that. Let's use a sine. So 2 sine. What are we going to put in for, let's see, the next letter is k. K times x. What is k? K is 2 pi over lambda. What is lambda? Okay, that's like how long for a cycle? 3. So 2 pi over 3. And what do we put in for x? X. It's an independent variable, right? We've got to write the x. So k is a constant, and in this case, it's 2/3 pi. So you got that by reading the graph. All right, smarty pants. Now, which way is it going? To the right, which means the sign in front of the time term is negative. I could spend all 70 minutes on that point. And after the lecture, somebody will say, now why does it go to the right when there's a negative sign there? Right? So, I'm a little time on it, but it doesn't really matter. Somebody will ask. And it's okay, please, I want you to ask, because then the story propagates. So we got to have some sort of omega here, but we don't know much about time. All we know is the speed. Well, the quick way is go to the physics version. Omega is vk. Right? So you can actually say omega is v. What is v? 6. And then you put in the k that you calculated before. You mean 2 pi over 3? Yes, 2 pi over 3. And you might say, well, how can I use the k in the time part. I don't understand. That's the whole point of how the wave works. The frequency and oscillation and the spatial oscillations are related. That's what the wave equation does. It relates the frequency oscillations in time to the oscillations in space by the velocity. So if you have need for omega and you don't know it, you can use k if you multiply it by the velocity. Right? So we use this same number here. And now what phase do we need? We need no phase. Because at time equals 0, it's a nice sinusoid. So we're not going to get into phase calculations yet. We'll deal with phase more later. So that's it, right? We could simplify it. What does this become? It cancels to a 2. It becomes 4 pi, right? 2/3 pi x minus 4 pi t. Okay, well, I wrote that in my notes, so I'm obsessive about this. So 2/3 pi x minus 4 pi t. There you go. So that would be the answer to part A. All right. Now, let's do a little trickier. Ooh, now, how can I make this unpleasant? Now, let's switch boards here. No. B, let's get the force on a piece delta x, at x equals 1.5 meters, or whatever unit it is. It doesn't really matter. Didn't really get into units. And t equals 0. What does that even mean? How am I going to get the force? Right, so this is the hard part, right? You can plug in chug for part A, but part B, you got to really know what's going on. Okay. This test, do you really know what this equation means? That's what we're really finding out here. I fear what the answer may be. Okay. So we're going to look at the thing and say, okay, maybe, by saying force, I guess I implied it's a string. Okay, so for part B, let's say it's a string, and these are vertical displacements of the string. I forgot. This problem implies it's a string. So we want to know the force on a little piece right here, delta x, right, at 1.5 at time equals 0. What force is that feeling? Well, you could probably maybe use your intuition and get it right, but let's do it mathematically. What do we know that's possibly going to give us the force? Kx, there's no spring constant k. There's only tension T. Somebody asked, what's K stand for? K is the wave number. K is the wave number. I just erased it. K is the wave number 2 pi over lambda. It's over there. So what we're going to do is, okay, so what do we possibly, can we get anything about that little piece, delta x? What can we get about it? We know its position as a function of time. So we know its position as a function of time. Maybe we could get its velocity as a function of time. Let's see. So that y is the position. What's the velocity as a function of time? Take a derivative with respect to time. Right? Say, okay, can I do that? I don't know. Let's see, 2. And sine becomes cosine. And the argument stays the same. Minus 4 pi t. And then how do I take a derivative of cosine? I have to pull out the derivative of this with respect to time. Stick it right there. Minus 4 pi. Right? So there's the velocity with respect to time. That's how fast that little delta x guy is moving at all times. Or this is how fast everything's moving at all time. We could put 1.5 in here and see how fast he's moving. Or she. Delta x is gender neutral. But we want the force, so it must be acceleration, right? So if we get its acceleration and we know its mass, that's how we can get the force. So we take another derivative. And get the acceleration of the whole thing. Cosine becomes negative sine, negative 2, negative 4 pi. We're going to pull another 4 pi out because we took another derivative. Squared sine 2/3 pi x minus 4 pi t. Interesting. Notice how we keep pulling out this one and not this one. It's because it's a time derivative. We're not taking a spatial derivative. We're taking a time derivative. Interesting. So there's the acceleration as a function of time. Very nice. Why don't we go ahead and simplify it? The acceleration as a function of time, it looks like squared becomes positive minus 2. So this minus hangs around. 4 times 4 is 16 times 2 is 32. Minus 32 pi squared sine of 2/3 pi x minus 4 pi t. Okay. So that's the acceleration everywhere. But now we want the acceleration of delta x. Now this is everywhere. But for the delta x in this problem, it's minus 32 pi squared sine 2/3 pi. Where is it? It's at 1.5. So now I don't have a negative extra negative sign. You have a negative extra sign. A negative extra sign, an extra negative sign. I don't have an extra negative sign. You have an extra negative sign. I hope after that display. I hope I don't have one because then it'll be embarrassing. Okay, so x, we just plug in x. What is a convenient version of 1.5? 3/2. I did that on accident. You're welcome. Okay. So 2/3 pi times 3/2. And then minus, and what is this one? We said at time equals 0. Okay. Now we are getting somewhere. So what is this whole expression? This is that whole. You got to be good at algebra and trig. Calculus doesn't really matter so much, except for taking the derivative. 0. Right? 2/3 3 sine of pi. What is the sine of pi? 0. So the negative doesn't actually matter. There you go. We're both right. Because this is going to be 0. So if that's 0, then what is the force? Well, if we want, we could put everything in. We could say, oh, well, it's mu that you forgot to give me times delta x times the acceleration. But it's 0 because the acceleration is 0. So it's 0. The force at that point is 0. Why do you have 2/3 s? There's a lot of 2/3 floating around in here. This is 2/3 pi because that's from way up there. So I'm not sure where you mean. Why do you have 2/3? There's not an s anywhere. So let's see. Physically, do we believe that the force is 0 on that thing right there? Yes. Because the person who is thinking of it as a spring is kind of correct. Basically, every little element of the string is kind of going in simple harmonic motion. And when something is in simple harmonic motion and it's at the neutral position, the force is 0. The kx is 0. Right? In a continuum like this, really every little element is feeling kind of like a spring force, but it's really from the difference of the two tensions along the string. Okay? What really happens, if we want to get deep down, do you want to get deep down for a second? What really happens is you have to think about how the tension is different. Like if I looked right here, here the tension is this way, here the tension is kind of that way. That slight difference in tension because of the curvature is what gives you a force. So you can see that here the tensions are perfectly symmetric. Right? So that's why the force is 0 there, which is also why it accelerates at 0 there. You might say, wasn't the force 0 here? No. Here the tension is kind of that way and it's kind of that way. There it's getting pulled up. So there's a relationship between the curvature and the net force due to tension. But that's beyond what we're doing. It's just your question inspired me to tell you that. I meant, where did 3/2 come from? Sorry, 3/2 came from, it happened at 1.5 meters. 1.5 meters is 3/2. All right. Is mu delta x like mass? Yes. So F equals ma. Mass density, and the little delta x has some size. Okay. Since the wave propagates is the same relative point on the wave, stay feeling no force through time? No. Right. That's why I said at time equals 0. So later, when, where's my damn board? Later, when, that didn't work. Later, when that part of the wave is up here, later when this is down here, it feels a force. Right? So it is like an individual part. It's kind of going through simple harmonic motion. Okay? And we would have got that answer if we didn't put 0 there. Right? If this had a value, would this sign have come out as 0? Probably not. Unless the value was pi or 2 pi. See, this is a good problem. Learning lots of stuff. Could you use v equals square root of t over mu instead to get t and then use that for a force? You could, but you screwed up, so don't do that. So what is moving at 6 meters per second? The wave is moving at 6 meters per second. So remember my video of the wave traveling down? It's moving at 6 meters per second. Don't make me show you the video of me trying to outrun a wave. Okay, it's really embarrassing. Okay. So that's an example of using, if you can do that, then you understand that solution, right? If you can figure out what omega is, what k is, and go this far, right? This is a calculus-based problem now. So this you have to be able to do. And then this would be like the little part at the end that's really hard, right? We didn't have any middle ground there. We just did the easy part, the straightforward part, and the hard part. Oh my God. No wonder we're so tired. Okay, yeah, so let's stop and we'll keep going. Oh, perfect timing.